Joshua is a founding engineer on the FlashBlade team at Pure Storage and is currently leading Pure's technical solutions in big data and deep learning. Previously, he was a data scientist on the search infrastructure team at Google, and he has a PhD in electrical engineering from Rice University. Please give him a big round of applause.
I assume everyone can hear me. I hope to not have to use the microphone. Great. Thank you for the introduction. I am going to talk today about two things, but both focused on storage in big data. So on one hand, I'm going to talk about and challenge a traditional way of thinking about how on-premise storage, for example, HDFS, works in big data. And the second is I'm going to talk about an internal use case, how we use tools like Spark, Kafka, and Elasticsearch while we, as software developers, are building our product, FlashBlade, and adding new features and trying to iterate and make it better. So quickly to set the stage, what our company does is we build all flash storage systems, high performance storage systems. We have two products. The first one on the left is a block storage, latency optimized, and it's our first product, started in 2008, I believe. The second product on the right, which is the one I worked on, is called the FlashBlade, and it is a scale-out file and object store. So this is where we come from. So we build these products, and we're software developers. So what it takes to build these things effectively, test them, make sure they work, that's the use case I'm going to talk about today. Now, when we're talking about infrastructure or applications for big data, there's a couple of pretty simple, high-level things we want. We want fast, we want big, and we want agile. So I think fast and big, to be honest, they're pretty self-explanatory. So throughout my presentation, I want you to keep in mind this agile. And I think that's really the key, is how can storage make you agile in building up your pipelines, your analytics, whatever systems you're using internally. That's the key. So I'll tell you really quickly a story I think you probably all know very well. And I'll frame it in our own use case, which is our product logs and our customer systems. So we have a lot of data. This is a long time ago. Different sources of information about our customers, what systems they have, what versions of software. And then all of the logs that was being generated, the phone home data, the telemetry, the performance data, that was being sent back from our customers. So a long time ago, we had a very old school way that we had built the system to understand and support our customers. So as you expect, what we did is when that was getting too cumbersome, we redesigned that system. We started using a new generation of applications that I'm sure you're all familiar with. You put Hadoop, Spark, and Kafka. We could combine all these different data sources, in particular the logs coming back from all of our customer systems, which is the large bulk of the data actually. Okay, so this was great from an application perspective, and it gave us a whole lot more flexibility in the kind of questions we could answer about our customer systems. If something was a problem, a customer was complaining about performance, we had a much stronger set of tools to quickly see historical trends, look across all the different systems that they have, across other customers. So from an application perspective, this is great and we were happy. But what about from an infrastructure perspective? From what we're actually running in the data center, what these applications, what the data is stored on, and that's what I want to talk about, because the traditional way is to have separate data silos for each of these different applications, Kafka, Spark, Hadoop, Elasticsearch, and that was causing us some problems. Okay, so when you think about what those problems are, we started with two applications, Kafka and Spark. Now, each of these is a set of compute and storage. So we have servers in our data center that provide both the compute and backing storage for these clusters, if you will. The traditional way of building these out is you have a separate silo of data for each of these different applications in your pipeline or in your data center. Then we wanted to do more things. We added more. We added Elasticsearch. We started building more systems as part of this because we were finding value for our customers and processing all the logs and providing support. So we want to keep growing. Then it keeps growing. So we have more and more silos of data. Each time we start to iterate, we try a new type of application. We want to build a second cluster to support different types of data. And this, from an infrastructure perspective, is really becoming a management headache. For all these different systems, you have to provision correctly, you have to manage separately, you have to upgrade. And for us, in our case, this was 6 petabytes of data from all of our customer logs. So it was growing. We're a growing company, more customers, more data. This is not feeling scalable. So let's talk about what we really want. What would be our dream? Let's fantasize. What we would really love to have is a separate set of compute nodes, so it's basically the CPUs and the DRAM, for all these different clusters, both the production ones and the QA ones and the development ones that we run alongside them. And we can do this with containers. I won't talk too much about that, but it's actually really cool. And then on the storage side, we just want something that's big, fast, and simple underneath that we can use to provide the storage, all the performance we need, all the concurrent access, and it can be shared. So we can consolidate applications. We can much more easily spin up a new container and create a new cluster. And by separating this out, so we're talking about decoupling the compute and storage, we have a much greater ability to quickly experiment with, change, and grow these systems. And that's where the product that we're working on comes in. That's the FlashBlade. So I'll really quickly tell you what that is. It's big, up to 8 petabytes in 20 rack units. It's fast, up to 75 gigabytes in that system, with 75 blades in it. And it's simple. And I'll not go into too much detail there, but this is kind of what our company's lifeblood is, really, building big, fast, and simple. It's surprisingly difficult to build simple, because that means everything internally has to be really complicated, which means you have a lot of work to do on the software development side internally to make it look simple from the outside. So that sets the stage of what we did for our internal use case. So now I'll talk about that software development that we do. So we have quite a lot of work to do to build this scale-out storage system that's high performance. This is not simple and easy. When I started, I was a little bit overwhelmed with kind of the complicated nature of how you build these distributed systems. So I'll set the stage with a problem. At the beginning, we first started 3.5, 4 years ago. It was a handful of developers. We had a handful of test boxes, hardware boxes that we could experiment with. We had a handful of VMs to generate traffic and do tests. And we really had one test coordinator, which means we had one branch, one feature branch. We just developed off master. We didn't have a product. We were just building something from the ground up. So it's a pretty small system, 100 tests maybe. This is what we started with. But fast forward to today, we have over 100 engineers working on new features for the FlashBlade. We have thousands of VMs that are running tests on the systems that we have. We have 120 actual test FlashBlades hardware in our lab. The VMs run simulators, so because even 120 actual physical hardware boxes isn't enough for all the tests we want to do. We have a lot more clients, and now we have a lot more test instances, which basically means we have a lot more feature branches, because we're developing a lot of different protocol support, or data services, or performance work, or new and faster NAND underneath. And these all happen in parallel. So we have a bunch of different code branches we're managing now, each of those running all these tests that we want to do, and different engineers working on different branches. So as you can see, this is a lot more complicated, a lot more tests being run. And how do we keep track of all these tests and the inevitable failures that happen? In numbers, what is that? So in numbers, that's 20,000 tests a day as of about 3 months ago that we run on our software branches. Now, we estimate about a 5% failure rate. Now remember, we're talking about testing basically head. So the latest, greatest, every time someone checks in a new piece of code, we're testing all of that. So this is long before we release our product, new features. And this is basically, the test failures can happen in multiple different ways. They can be a code bug, a real legitimate bug. Or remember, we have racks of data center equipment. A switch could have failed, which causes all these downstream effects on all the FlashBlades that are connected to that switch, or all the clients that are connected to that switch. Now, in a real customer environment, we can handle that because we have redundancy built in. But in our test environment, we want to make sure anything that happens that's not expected, we flag it, because it could be a real bug, and we have to always check. We have to dig deep and make sure that no real bugs come out and get released. So we estimated if we had people looking at those 1,000 failures a day and trying to figure out, okay, why did this test fail? What was the root cause? Why did this test fail? What was the root cause? That would basically require 20 engineers full-time job to triage all of those failures. And I think we all know that that's just not going to happen. That's just not practical, and it's not scalable. Because a lot of times what happens is one bug causes 14 different failures, or one down switch causes 300 failures. Because these systems are all complicated, and they fail in slightly different ways, but the root cause may be the same. So we need to be able to track all these failures down, so no bugs, but there's a lot of duplicate failures. And of course, to make things worse, we're a growing company. We expect this to double in the next 12 months. So clearly, I think we can see this is not going to work. This is not a great solution, just manually having engineers triage all these failures. So the dream. What's the dream? Let's talk about the dream. The dream is automate the triaging of failures. So once a problem is identified, we can automatically tag all the subsequent failures. This is why this failure happened. We want to extract performance metrics so we can continuously monitor and check for performance regressions from all of our test systems that we're kind of beating up, to be honest. We want to save the logs for future use because somewhere down the road we may realize, oh, actually something's been happening that we didn't pick up on. Let's go back and look in the past to see when it was introduced. Something kind of subtly sneaks in. We want to do all this, of course, in a scalable system so that 2 years down the line, we still keep doing it and can still keep developing new features at any kind of pace. And of course, real-time results. We want to be able to quickly triage these failures because they start to happen fast when all these 20,000 tests are running a day. So what did our pipeline start with? Back in the early days, we had 10 FlashBlades, and we were using our syslog to collect all the log lines from those systems under test. So we had a kind of dedicated compute resources to that. You know, there's a lot of extra context we need. There's a lot of transformations to log to make them understandable by the machine. So we did some Google searches and Logstash. That seems to be the tool of choice. So Logstash processed the logs, and we used Elasticsearch to save and index those so we could later search them and basically do useful things with those logs. And of course, Kibana, we use that to kind of look at the performance graphs and examine the data we have. And this worked well at the beginning when we had our initial system. Now let's fast forward now. Let's say we have back when we had 1,000 tests running a day. How did that change? Well, our syslog actually kept up great. It's just basically piping the log lines out from these test systems, but we're piping it into Logstash. And Logstash, we were finding we really needed throw a lot of cores at Logstash. We were doing a lot of transformations, and it wasn't keeping up. So it was the big resource hog as we started to scale out. Elastic we needed to scale out some as well, but not as much as Logstash. So our first bottleneck here was Logstash and the amount of processing. Now one of the the downstream effects of logstash kind of not being able to keep up is we would start to drop logs at rsyslog. So we would just kind of have to drop them and forget about them. And that's, as I'm sure you can guess, that's really frustrating when you're trying to debug an issue and you realize the logs just didn't make it out. So you're not able to debug because you lost data because rsyslog, well, because logstash wasn't keeping up, causing rsyslog to drop packets. So the first thing we did is add Kafka. And that helped us to buffer those logs if logstash wasn't keeping up. So we weren't dropping packets, or sorry, dropping log lines. Kafka was helping us to basically provide a buffer there. But ultimately, it turned out that logstash just wasn't keeping up, and we were trying to do too much with it, and so we rewrote that logic and we used Spark. And Spark became the core of our ETL pipeline where we took the log lines, annotated them, what test was running, what rack is this test running connected to, and that actually was. My background is I worked on MapReduce forever, 2.5 years every day. Spark is great. I loved it. It was so much more fun. I really enjoyed working in Spark as compared to the old MapReduce stuff. That's a personal note, though. Elastic still kept up pretty well, but it was now kind of the biggest resource hog in the system. Again, let's go forward. Now we have 4,000 tests running. We needed to scale out a little bit, but we were finding that Elasticsearch ingest on Elasticsearch wasn't keeping up. We were having a hard time keeping the load balanced across all of the nodes in Elasticsearch. And it was now that Elasticsearch is the resource hog. It's the scalability limit in the system. So what we have today. So this is now we're talking about what we have today. This is the full system, what we have. With 20,000 tests. Now rsyslog is still keeping up. We have 16 cores per system instead of 12 now, so we scaled it a little bit. But it's working great. You'll see here the numbers. So it's 6 terabytes of raw logs are coming out a day. After the adding of context, what test is running, what system is it running on, it's 18 terabytes of data a day that goes into Kafka. And then that's the 18 terabytes that gets fed into Spark. There's a Spark streaming job where we process all of these new log lines as they come in. Now we were finding that's too much data to put in Elasticsearch. It definitely wasn't keeping up. So we actually used Spark as a filtering layer where we trimmed out data, we slimmed it down, we picked out the data that we really needed, and as the output of the Spark is 6 gigabytes a day of data that we're feeding into Elasticsearch, mostly performance data. Performance for all types of internal systems inside of our storage system. Now, I'll get back now. So all of this, you've seen just the compute. All of this is actually running on one FlashBlade system. So all these different systems, and actually all the different iterations I showed you, we're all still running on that same common shared storage backend. We never had to worry about the storage. We could try different experiments. We brought up Kafka. We changed our Spark clusters. We brought up test Spark clusters, all on that same single piece of storage, centralized storage that we were using, which happens to be a FlashBlade, which is also happens to be what we're trying to make better. So coming back, I was talking about this automated triage, right? So how did that work? So what we did is we put a little bit of custom code that hooked into our output of our Spark job to basically build fingerprints so that we could detect, once we've first time determined a failure, we update this custom code with a fingerprint, and it can start flagging all subsequent failures that match that fingerprint, that failure signature. And we did that with custom code, which is actually a relatively small, straightforward kind of set of Python scripts to do the actual fingerprint, and it interacts with our other tools in our system. So it finds duplicate bugs. It knows about infrastructure failures because there's VMs that are misconfigured, switches that fail. We want to know about all these and not flag those as errors or infrastructure errors. And we used Kibana, Jira, which is our bug tracking tool that we use to track the fingerprints. And of course, Jenkins, and the custom code interacts with these other components, Jira and Jenkins. So at the end of the day, this is what we're running today as our pipeline. Just to give you a little more of a sense of the numbers, which is for sense of scale, I think you probably can't tell on this dashboard very well. So we're processing 18 terabytes of data a day on that single FlashBlade. That corresponds to 30 billion events per day. And it's constant throughout the day because basically our systems are always running the latest tests that they can. We keep them running basically 24 hours a day, if at all possible. And then we extract 6 gigabytes a day, which corresponds to 8 million events. So the contrast here is instead of having these 20 engineers trying to triage these 1,000 test failures, we have our pipeline, and what happens now is we just have about 30 distinct test failures a day. That's our estimate. It varies widely, but that's about the average. And for that, we have one engineer who's dedicated to these triage. And that is a much more scalable solution, and it helps us basically develop features faster. We're able to make more code changes, improvements, add more features, because those 19 engineers aren't triaging failures, they're writing new code. So I'll end this with a little bit of a brief description of what are the benefits of using shared storage instead of having nodes where the compute and the storage are together, coupled together. And this is where we really found the agility and the flexibility beneficial for us in our use case. So about scaling storage, originally we started with a much smaller set of systems. We did not need nearly as much storage. But as we grew, we needed to add more storage. So what did that involve? So for the FlashBlade, let's see if my video works. This is a shot of the FlashBlade GUI. It's a 230 terabyte system. 260 terabyte system. And here's the video. To increase the capacity, we just slide a new blade into the system. And within the next minute or so, all of that new capacity is now available to all the applications. Kafka, Spark, Elasticsearch. They all see that new capacity. We've at least doubled the size of the system throughout this process that I walked you through. And it was as easy as that, sliding it in. Done. Scaling compute. I talked a lot about, okay, our syslog is scaling well, but we needed a whole bunch more Logstash servers, and then Elasticsearch was growing. How do we do that? So, for example, we started with this, where we were outputting 4 gigabytes a day. We wanted to start collecting a little bit more log lines, back to the 6 gigabytes a day I mentioned. So the process there, download a Docker image on one of the hosts, mount the FlashBlade within that container, and then we can add it to the cluster. And that's a little bash command that we have that it took about 2 minutes. We can grow the Spark cluster and a process as simple as that. Same is true with Kafka and Elasticsearch and other applications that we're experimenting with, but I'm not going to talk about. So and that really allowed us to basically say, okay, we'll add 2 more of these servers to our Spark cluster. We'll start outputting 6 gigabytes a day because we want to start collecting more data. And it was as easy as that. And that's the ability that we just needed more compute in this case. We didn't want to store more data. We didn't want a new node that also came with a bunch of storage attached to it, just more compute. And that flexibility lets us better provision our resources in our system. We're not wasting resources that way. Another example of a great benefit is the agility to do ad hoc analysis. So we have our system with all our components, and sometimes what will happen is we'll discover a performance regression. Where did that happen? It was kind of slow and subtle, or it was only on a certain corner case. And so we can spin up a Spark cluster to do a one-off analysis. We want to look through all of that historical data and find where that regression might have started. So this is an example. We brought up a 1,000-core Spark cluster, churned through all of the historical data looking for when that regression occurred. And it was really easy to do without any kind of change to the storage system. The storage system was able to handle both the production pipeline as well as these experimental systems at the same time. And now it's just a matter of what compute do I need? What compute resources do I need? Simplicity. This I'll go real quickly. this is the benefit of having something like an all-flash, purpose-built scale-out system. You have much less rack space. It's a much smaller system. A lot fewer things can fail because you don't have moving parts. Management is much easier. You can just upgrade the storage system non-destructively, independent from all your Spark jobs or whatever else is going on in your cluster. You can now just independently manage that storage side. And you also get access to data features like snapshots and other types of backup and management for your data layer that come with having a centralized all-in-one-place storage tier. So that's the end of the talk. I don't know how much time I have for questions. I would love to have.
You have 4 minutes.
I have 4 minutes for questions. If you have questions about the use case we have, or especially the difference between using shared storage versus kind of a coupled direct attached storage model, or find me afterwards, feel free to ask. Yeah?
FlashBlade is direct attach, or is it SAN, or is it
It's not direct attached, so it's the shared storage. So it's let me go back to my. I didn't go into too much detail because I didn't want to make it too much about a product pitch. So all of these systems talk to the FlashBlade over basic IP Ethernet. So it's an IP address.
NAS device?
It's a NAS device. It's either NFS or it's S3 for object storage if they want to talk, whichever protocol they want to talk. And they're just connected via the network.